Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing BGP, concepts, configuration, and monitoring in Junos. In this lesson, we'll be doing a lab demonstration, covering the configuration and monitoring and troubleshooting of eBGP and iBGP. We'll configure a router to participate in iBGP using the type command. And then we'll configure another router to participate in iBGP using the peer AS commands. In both cases, we'll then review the neighbor states and routes received. Next, we'll configure the same two routers to participate in eBGP and set some commands to ensure the necessary routes are advertised and prepend the AS from one of the routers so the other path is preferred, and check the route table from the ISP router to validate it's being received as intended. Finally, we'll configure a next hop self policy to ensure the externally learned routes are reachable from our enterprise internal routers, and we'll validate this takes effect. So, just like our other lab demonstrations, let's review the target diagram for this lab before we go over the instructions in more detail. This lab demonstration is a fair bit larger than the other labs we've done. We have our enterprise environment at the bottom with 3 routers in AS65500, VSRX1, VSRX2, and VSRX3. VSRX3 has 2 virtual router routing instances configured, and each instance here shows to have an enterprise server with a public IP address attached. In reality, 1.1.1.1 and 2.2.2.2 are additional IP addresses assigned to the loopback interfaces in each instance. This is to simulate having a publicly accessible set of servers within our enterprise that will want to be routable from the internet outside of our own AS. The routers in our enterprise are all running ISIS as their underlying IGP. Though we have iBGP configured on VSRX3 currently, VSRX1 and 2 are not yet participating in AS65500. So we'll be configuring them during the lab. VSRX1 and 2 also connect to public internet service providers, ISP-A and ISP-B respectively. ISP-A and B are both configured to form eBGP peering sessions with our enterprise's edge routers already, though VSRX1 and 2 are not yet configured to participate in eBGP. To simulate an actual enterprise edge environment as much as we can, we've used public addressing at the edge for our connections to our public internet providers. Finally, we have a third internet service provider, ISP-C, in AS65530 at the top of our diagram. This ISP originates a public address 8.8.8.8 that we'll be using to illustrate eBGP routing across autonomous systems and validate reachability to this distant prefix from within our enterprise. ISP-A and B have eBGP peering sessions formed with ISP-C already, so they will exchange all routes in the BGP routing table. Great. Let's now review the instructions for this lab before we jump in and start configuring. The first section of this lab will involve the configuration and monitoring of iBGP peering sessions and routing. As per usual, we'll start off by reviewing the starting configurations on our enterprise devices. We'll review the starting configuration on VSRX 1, 2, and 3, as well as take a look at the current routing tables on 1 and 2 to better understand how this changes after iBGP is configured. We'll start off with configuring iBGP on VSRX1, setting the autonomous system number to our enterprise's AS, and configure our IBGP neighbors of VSRX2 and both instances in VSRX3. On VSRX1, we'll use the type command to define these sessions as IBGP sessions. And once committed, we'll take a look at the peering session status and routes received on VSRX1. Next, we'll move on to VSRX2 and proceed in the same manner. We'll set the autonomous system number to our enterprise's AS and configure our BGP peering sessions with VSRX1 and both instances on VSRX3. On VSRX2, however, we'll use the peer AS commands to define these as IBGP neighbors. Once committed, we'll review the neighbor summary and routes received on VSRX2, since we now have a full mesh of IBGP peering sessions established. That'll conclude the IBGP configuration and monitoring section. Next, we'll move on to configuring and monitoring eBGP. As for the configuration and monitoring of eBGP sessions, we'll start off on VSRX1 and configure our peering session with ISP-A. Recall that the primary purpose of this eBGP peering is to advertise our enterprise public servers, 1.1.1.1 and 2.2.2.2, to the Internet. Once configured, we'll review the advertised routes and find that we're not yet advertising these routes. We'll explore why briefly, and then configure the advertise inactive flag and validate this has been resolved. We'll then move on to VSRX2 and configure its peering session with ISP-B, remembering to include the advertise inactive flag since the same situation that required it on VSRX1 will be present on VSRX2, as we'll see. We want to prefer ISP-A for inbound traffic, though. So, we'll go back to VSRX2 and configure AS path prepending for our routes advertised to ISP-B. Once committed, we'll jump back to ISP-C briefly and validate the change took effect and how the enterprise routes are now shown in ISP-C's routing table. And that will conclude our configuration and monitoring of eBGP section. We'll move on then to the last section of the lab, configuring and applying a next hop self routing policy. Our first step in this section of the lab will be to review the routing tables on VSRX3 in both instances for the 8.8.8.8 route that we should expect from ISP-C. We shouldn't see the route as the protocol next hop will be unreachable, and we'll show a command we can use to view the route anyway to validate it's being propagated through BGP. The following steps will resolve the protocol next hop being unreachable by configuring a next hop self policy. On both VSRX1 and 2, our enterprise edge routers will configure a BGP export policy and apply it to our IBGP group to change the next hop of externally learned routes to their IBGP peering address. Once complete, we'll head back to VSRX3 to check our work and validate the entries for 8.8 are now showing active and reachable. And that'll be it. Without further ado, let's jump on in and get started. We'll start off with reviewing the current configuration on VSRX1. As usual, we have the lab user configured and other default configuration below. Moving down, we see our management interface at the top and other production interfaces below. We see that GE003 is our interface connected to ISP-A, with the other interfaces connecting internally to VSRX2 and 3, each with the ISO protocol family enabled to participate in ISIS. Moving further down, we have the loopback interface and a static route for management access. Then, we have our ISIS configuration already in place, with all of our internally connected interfaces participating, as well as the loopback to facilitate our impending IBGP configuration. We see on the loopback's NET address that VSRX1 is configured in ISIS Area 51. Level 2 is disabled, however, for the entire ISIS protocol. As we'll see on the other routers, the ISIS domain in our enterprise is a single area, with all routers participating as Level 1 routers, as is typical for a small to medium-sized enterprise environment. Finally, we'll have our packet mode configuration at the bottom. Let's now move over to VSRX2 and review the starting configuration there. Similarly, we have the lab user configured and default configuration otherwise towards the top. Moving down to our interface configurations, we also have the management interface at the top and other production interfaces below. We see that ISP-B is connected to VSRX2 on GE003, and the other interfaces, like on VSRX1, connect internally and have the ISO protocol family enabled to facilitate ISIS communication. Next is the loopback interface. We see that VSRX2 is also configured in ISIS Area 51 as expected. We have the static route for management access, and our ISIS protocol configuration, which is identical to VSRX1, and finally the packet mode configuration at the bottom. Great. Finally, let's move over to VSRX3 and review the configuration there before we start configuring VSRX1 and 2. Just like VSRX1 and 2, we have the same lab user and default configuration at the top of our hierarchy. Moving down to the interface configurations, we again have very similar configuration with the management interface GE000 and other production interfaces below. Note, as in previous lab demonstrations, we have two logical units configured on the loopback interface, one for each virtual router routing instance configured on VSRX3. We see the ISO protocol family is enabled, and the VR11 unit is in Area 51. Note here, however, that we have a secondary IP address configured on the loopback interfaces. In our diagram, these are represented as the servers connected to the VR11 and VR12 instances on VSRX3, which are simulated by loopback addresses being distributed into BGP, as we'll see a bit lower in our configuration. Moving further down, we have the remainder of the VR12 logical unit configuration with the 2.2.2.2 IP address and ISO NET address configured as Area 51. We have the management static route and the routing policy below, which distributes our simulated server IPs into BGP. These policies, VR11 BGP and VR12 BGP, use a route filter to match the 1.1 and 2.2 routes exactly, and will accept them. As we'll see in a moment, this will be applied as an export policy in the BGP configuration, so that the routes will be distributed into BGP. We then see the packet mode configuration before moving down to our routing instances configuration. Here, we see the VR11 instance. It is a virtual router instance and has the GE002.0 and Unit 11 of the loopback added. Something new to this lab is the autonomous system configuration and BGP protocol configuration. VSRX3 is within our enterprise AS 65500. In our BGP configuration, we're using the loopback address for this instance as the local peering address. And we have 3 neighbors configured with sessions to the loopback interfaces of VSRX1 and 2, and the VR12 instance of VSRX3. We see that our export policy is applied here at the group level of the configuration to distribute our simulated server address into BGP. Our peering sessions are using the peer AS statement to indicate that these are iBGP peering sessions within the same AS as the local router. Finally, we have the IGP configuration below, providing the loopback connectivity for the BGP peering sessions to operate. When we move down to the VR12 instance, we see a very similar configuration, with the interfaces and BGP neighbor address adjusted for originating from the VR12 instance instead of VR11. Excellent. Let's now take a quick look at the routing table on VSRX 1 and 2 before we get on with our configuration changes. Here, we see that we have ISIS routes showing, along with our simulated server routes. Since the loopback interfaces which have these addresses are passive interfaces participating in ISIS. Otherwise, we see the loopback interfaces for each of our enterprise routers, so we should be good to go. Similarly, on VSRX1, we see the equivalent routing information, with the simulated server addresses and the loopback interface addresses in the ISIS protocol table. Great. Let's move back over to VSRX1 and start configuring our iBGP neighbors. We'll set the local device autonomous system as our enterprise AS 65500. To organize our configuration, it's best practice to group your BGP neighbors into sections that are operationally similar. In this case, we're grouping our iBGP neighbors into an iBGP group. We'll configure a neighbor statement for each of our enterprise routers and set the local peering address as the loopback interface address of VSRX1. Notice that we did not configure the peering type statement, nor a peer AS statement to define the type of BGP peering session, as indicated in our commit error. Let's set the type for our iBGP group to internal and try again. Great, that committed successfully. So let's check our BGP peering session summary to view the state of our sessions. BGP is notoriously slow as a protocol. Even though it is a very scalable protocol, it can be a bit slow to establish. We see here that all three of our peering sessions are in the active state. This means that the TCP session has not yet been established. However, now that we've waited a bit of time, if we execute the show command once more, we see that our peering sessions with VSRX3 are now established. And, as expected, our VSRX2 session has not yet established, since we still need to configure BGP on VSRX2. In this output, we see the statistics information on each configured peering session. From the left, we have the configured neighbor address and the AS of the peer. Since the group was configured as internal, all of our configured neighbors are showing as being in the enterprise AS. The following two columns show how many BGP packets have been sent and received for each peer. Then we have the out queue of BGP update packets, which are queued to be sent to the peer. The flaps column would show how many transitions from established to not established that this peer has seen. Then the up-down column shows the amount of time that the peer has been in the current state. If the peer is currently not in an established state, then it'll show the amount of time that the peer has been down. If it's in an established state, then it shows the amount of time the peer has been established. These are in seconds currently. However, the unit displayed will change once the time becomes sufficiently large to indicate days, hours, and minutes. Finally, in the last column, if the peer is not yet established, as is the case for the VSRX2 peer in the top row, this column will give us the state of the peering session. If the peering session is established, as is the case with the VSRX3 peers below, we have some prefix statistics. for the inet.0 table on the left and the inet.2 table on the right. As we can see in the column header, these numbers indicate, from left to right, the number of active prefixes, the number of received prefixes, the number of accepted prefixes, and the number of dampened prefixes. An active prefix is one that is an active route in the local device's routing table. The number of received prefixes is the number of prefixes received in BGP update packets from the peer. However, even though a prefix is received, doesn't mean it's accepted. The prefix could be dropped due to a loop prevention mechanism or some other mechanisms. Thus, we have the accepted column indicating if all of the received prefixes were accepted. Finally, the dampened column indicates the number of prefixes whose state has changed quickly, causing Junos to dampen the prefix. This is BGP's method of mitigating the effect of route flaps. If a route flaps a certain number of times in a given time period, then Junos will stop processing state changes for the route and begin a timer to dampen the flapping route. Excellent. Since we see we've received and accepted 2 routes from our VSRX3 peers, let's take a brief look at the routing table to see those BGP routes. And there we are. Using the show route protocol BGP command, we can see all routes in the routing table which are in the BGP protocol. We have the routes present in the inet.0 table for the 2 simulated servers connected to VSRX3. We see that there are 2 paths to 2.2 since we have equal cost IGP paths to the VR12 instance over the 2 links connected to VSRX2, GE001 and GE002. Note, though, that neither of these routes are active. This is because of the default preference value for BGP, which is 170, shown here. We also could note in the BGP summary command above that 0 of the routes received and accepted for each peer are active. Since the routes are also being learned by ISIS, which has a default preference value of 15, the ISIS learned routes are preferred and therefore selected as the active routing entries. Let's now jump over to VSRX2 and finish our iBGP configuration so we have a full mesh of peering sessions. We'll use the peer AS configuration statement here to define the AS of our configured BGP neighbors. This is the same AS as the local device, defining them as iBGP neighbors. And we'll set the local peering address to the loopback. So, now when we run the show BGP summary command, we see that all 3 configured neighbors are in the active state, just like we saw over on VSRX1. However, if we wait a few moments and run the command again, we now see that all 3 peering sessions are established, and we've received and accepted a single route from each peering session with the VSRX3 routing instances. Let's just take a look at the BGP routes here before we move on to the next section of the lab. Just like on VSRX1, we see both of the simulated server IPs in the BGP table. And also, just like on VSRX1, neither of the routes are active, due to the protocol preference of BGP being higher than ISIS, where these same routes are also present. Excellent. Now that we've configured VSRX1 and 2 to participate in iBGP, we have completed our full mesh of iBGP peering sessions. So we can move on to configuring our enterprise edge routers, VSRX1 and 2, with eBGP peering sessions to our internet service providers, ISP-A and ISP-B. So let's hop back over to VSRX1 to start our configuration. We'll configure a new group in the BGP protocol hierarchy called eBGP and configure our ISP-A neighbor and set the peer AS to ISP-A's AS, 65510. That's the only configuration line that's necessary to configure an additional BGP neighbor. So we'll go ahead and commit this. We'll take a look and confirm our newly configured peer is showing in the output of Show BGP Summary, though it's in an active state. So we'll give it a few moments to come up and run the command again. And there we go. Our eBGP peering session with ISP-A is up. Notice that we've received and accepted one route from ISP-A, and that route is actually active. Let's see if our simulated enterprise server routes are being advertised to ISP-A. We use the show route advertising protocol BGP command along with the neighbor IP address to validate what routes are being advertised to a BGP neighbor. Notice that this output is empty, indicating that we're not advertising anything to ISP-A. This is because the default BGP policy will only advertise routes in the BGP protocol which are active in the routing table. Let's confirm what route we're receiving from ISP-A. We use the similar command, show route receive protocol BGP, along with the neighbor IP address to validate what routes are being received from a BGP neighbor. Here, we see that we're successfully receiving the 8.8.8.8 route from ISP-A, and this route is active, as is indicated by the asterisk next to the route entry. Notice on the right that the AS path shows the route passed through ISP-C's AS 65530 and ISP-A's AS 65510 before reaching our enterprise AS 65500. Reviewing the routing table once more, we see that although the 1.1 and 2.2 routes are present in the routing table and in the BGP protocol, they are not active in the routing table due to having a higher preference value than the ISIS learned routes to the same destination. We can override this default behavior by setting the advertise inactive configuration statement. This statement can be configured at the protocol, group, or neighbor level. In this case, we're applying it at the group level, so it would apply to all configured neighbors in the group. And there we go. We now see that the 1.1 and 2.2 prefixes are being advertised to ISP-A, who will then re-advertise it on to ISP-C or any other upstream providers. Let's now jump back to VSRX2 and configure our eBGP session there. Our enterprise prefers ISP-A for inbound traffic to the enterprise, though we want to maintain our connection to ISP-B as a backup connection. Because of this, we'll deprioritize our enterprise routes advertised to ISP-B by prepending the AS path, therefore making those prefixes less preferred. We prepend the AS path by configuring a routing policy. This policy is named AS prepend, and the term called term 1. We'll set this policy to match all routes in the BGP protocol, as this will be applied as an export policy to the neighbor configuration statement for ISP-B. We'll prepend our AS to the AS path 3 times. The AS path to prepend must be in quotation marks, and the ASNs to prepend are separated by spaces. Moving back up to the top of the configuration hierarchy, we'll now configure the ISP-B peering session, with the neighbor IP and peer AS for ISP-B. We'll be sure to configure the advertise inactive statement here as well to ensure the 1.1 and 2.2 routes are indeed advertised to ISP-B. And we'll set the export policy on the ISP-B neighbor and commit. Great. Now let's check to confirm the peering session comes up. Just like before, we've caught it in the active state. So if we give it a few moments, we should see it come to established state. And there we go. Let's confirm our enterprise prefixes are being advertised to ISP-B and that they have their AS path prepended as intended. And there we have it. We see both 1.1 and 2.2 are being advertised to ISP-B. And looking to the right, we see the AS path attribute on both of these routes includes 3 entries of the 65500 AS, our enterprise AS, to influence inbound traffic to the enterprise to take ISP-A over ISP-B. Let's jump over to ISP-C briefly and confirm how these routes are showing there. Great. Here, we see only the entries from ISP-A, where we have a single instance of the 65500 AS in the AS path. This is expected, since the BGP protocol will perform the best path selection and will not insert the suboptimal route into the routing table. Finally, let's validate that 8.8 is reachable from within the enterprise and make any changes needed to ensure full connectivity. This output is empty, meaning we don't have a route present for the 8.8.8.8 destination, even though we confirmed we learned the route from both ISP-A and ISP-B. We can use the all flag at the end of the command to display hidden routes as well. Here, we see that the 8.8 prefix is indeed being learned in both the VR11 and VR12 instances. However, the route is hidden. We see below the AS path attribute the reason why the routes are hidden, due to being unusable. This is due to the protocol next hop address being unreachable, as VSRX3 doesn't have a route to the interface IP address of the ISP-A or ISP-B routers. Let's go back to our edge routers and configure a next hop self policy to ensure the rest of our enterprise can reach routes learned from the external BGP peers. We'll create a policy named nexthopself and a term named term1. We'll match routes in the BGP protocol, which are learned from external BGP peers, and apply the then statement of nexthopself to modify the nexthop attribute to be the local router's peering address with other BGP peers. This policy is set as an export policy in the iBGP group. Great. And now let's do the same for VSRX2 to ensure the prefixes learned from ISP-B are also reachable from within the enterprise. And finally, if we check the routing table once more on VSRX3, we now see that the 8.8.8.8 prefix is no longer hidden in both routing instances and is active, since the protocol next hop is now reachable. This concludes the BGP Lab demonstration. I hope that this lesson has been informative for you, and I would like to thank you for viewing.